Hello everyone. So what I want to do today is take some time to make a connection between Hooke's law and the energy stored in this system. So I guess the first thing to know, we have our classic setup of our spring on with a mass attached to it. And remember, it's oscillating back and forth, right? So remember, we can plot this oscillation, right? We have some x-axis. And let's say it starts at A, right? And this is our time axis. Remember, we have to tilt our head to look at this. But as this thing oscillates, right, it goes back and forth and follows this cosine. Well, what can we say about the energy when the spring is at this point, right? Well, when it's at this point, all the energy must be stored in the spring. Like, the mass isn't moving. There's no velocity. We're not accounting for gravity in this situation, right? Gravity's pointing in this direction and isn't really affecting the system. The potential energy with gravity stays the same the whole time. At this point, all energy is in the spring, stretched, right? Because there's no velocity. But when the spring starts to move and it gets to its equilibrium position, it's not pushing or pulling in either direction, right? There's no displacement from x. So it must mean that all of the energy is now in velocity. And remember, it's at this point where we have a maximum velocity in our system. All energy in velocity. Just remember Hooke's law, when it's at its max, all the energy is in the spring. When it is zero, right, when x is zero, all the energy is in velocity. So I'd like to think about this in another way. I'm just going to copy and paste this. I want to think of this in another way. I want to think of this in terms of the actual function we could use to describe the energy. And to do this, I'm going to use a really fundamental relationship. So the fundamental relationship is that the force in the x direction is given by the negative derivative of the potential energy with respect to the same direction. So this is a really, really, really important equation that I don't think is rarely talked about. One that you might see in the textbook a lot is something like work is equal to the derivative of f dx. So these are sort of the same formula. But this one involves an integral. I think it moves a little too far. I like thinking about it in terms of this relationship. And this relationship is really, really fundamental. So I'm going to put a big box around it because it's so fundamental. And when you get into later calculus courses, you'll realize that this is part of a very important theorem that talks about path independence and all kinds of stuff. And so what this says is that if a potential exists, if a potential energy exists, this is how you would find the force from that potential energy. But we're going to do the reverse. We're going to think, well, I have my force. I know it's Hooke's law. And what I want to do is think, well, what could my potential energy be that gives me this force, right? I've displaced my mass by some amount, x, and I have this force. What potential energy gives it to me? And the thing to do is just to think of like, well, what is the antiderivative of this? We know that I'm looking for negative k times x. And I know that if I take the derivative of u and times it by a negative sign, I must get f of x. So what do I take the derivative of to get x? Well, I take the derivative of x squared to get x, right? But when I take that derivative, well, what happens? I take the derivative of x squared and a 2 drops down, right? So I need a 1/2 in front of this to cancel that. Well, what else am I missing? I take the derivative of this, and I get just x, and then I multiply it by a negative sign. Oh, I got my negative sign. I just need to add in the k, right? So let's just put the k here. So the potential energy looks like it's k over 2 times x squared. So let's just try it out. So, and see if we reproduce Hooke's law. So negative du dx is equal to negative times the derivative of k over 2 x squared is equal to negative kx times 2 divided by 2, and the 2's cancel out, right? Which is equal to f of x. So for Hooke's law, this is also a really important equation. This is the energy stored in the spring. Energy stored in the spring. So now we're ready to talk about the total energy of this thing. So what is the total energy? The total energy at every given point is E total is equal to the kinetic energy of the system at any given point plus the potential energy at any given point. And what is this equal to? Well, the kinetic energy is equal to 1/2 mv squared. So it's the velocity of the block at any time plus 1/2 kx squared. So this is our general form. And we'll note two things. When x is equal to 0, so when the spring is in the middle, right? The spring is in the middle, we know that there is no energy, right? There's no energy from this. The total energy is equal to 1/2 m. And what do we know about the velocity when it's at the middle? It's at its maximum, v max. Well, also when x is equal to a, its total amplitude, well, what do we know about the velocity when the mass is way out here? Well, now the velocity is 0, right? It's stopped and it's turning around. So the E total is equal to 1/2 k times now the amplitude squared. So we have three relationships here. We have this relationship, which holds at all times, right? The total energy is always equal to this. And then we have two special cases, right? We have where we can find the total energy. If we know what Vmax is, we can find the total energy by plugging into this. And if we know what the amplitude is, we can find the total energy by plugging into that. And right, I guess one thing to note is that while the system is going, we can look at a graph of energy. At its extremes, the potential energy looks like this. And so this is U. And throughout the motion, the kinetic energy looks like this, right? And we always have the same total energy, right? So they always add together, no matter where they're at, to get the same total energy, right? This curve adds with this, and we see that it gets there. When this is 0 and this is total, we see that it adds to the total energy, right? So there's an interplay between these two things. Okay, so that's Hooke's law and energy.